Okay, guys, so in this video, we are going to go into the Avogadro's law. And so what the Avogadro's law now establishes, guys, is let me first write the name of the law, Avogadro's law. So what it does, guys, establishes a relationship between the volume of a gas and number of moles. So there's a direct relationship between the number of moles, guys, and the volume of the gas. Or it can also express it as K times N. Now, so why is this law important? This law actually has several implications here, which we actually used. Now, based on this law, we're able to determine, guys, the relative masses, which are used in periodic table. For example, when we choose, for example, carbon-12 isotopes to be a mass, like a standard mass against which all other masses are referenced to. So the Avogadro's law now helps to establish what's called relative masses now. So how does it do it? Now, the Avogadro's law, again, it states that the volume of a sample of a gas is directly proportional to the number of moles in the sample at a constant temperature and pressure. So here I have to also mention at constant temperature and pressure. Now, but what is the importance now on the microscopic level of this law? Now, what's important here for you to realize is that, let's say we have this chemical reaction, like 3H2 gas reacting with, let's say, 1 molecule of N2 gas. It's going to produce now 2 molecules of ammonia gas. So what this law is telling you guys, kind of indirectly, is that if you fill a balloon here, let's say, a balloon here with hydrogen gas, let's say you got a hydrogen gas here, and you got a balloon here with a nitrogen gas, okay, with a nitrogen gas. So what I try to do, let me just erase the first balloon to make the second one and the first one, guys, of the same volume to make the point here. Let's say these are the same volumes here, V1, this is V2, and then V1 is equal to V2. So what this law implies, guys, supposed to be N2 gas, is that as long as the volumes here are equivalent, the same, so what you got here is that you have exact same number of hydrogen molecules of gas occupying this balloon as the same number of hydrogen gas occupying this balloon will be the same gas molecules of nitrogen here occupying, guys, pretty much the same volume. So this balloon and this balloon will have the same number of molecules of each gas. That's what the now importance here of Avogadro's law. And if you now pump, let's say, ammonia gas in here, as long as this is the same volume here at constant temperature pressure, you should really get now V3 now will be also equal to now V2 and V1, and it will also have now NH3 now having the same number of molecules of ammonia gas as the N2 gas, as H2 gas. So how does it help you guys now with the reference, with the relative masses? And the way it helps is to realize if you go to the subatomic level, and let's say you have 3 molecules of hydrogen, and then you're going to draw a certain volume now, here you got 3 molecules. So what's interesting now, what's fundamentally interesting now with this Avogadro law is that, let me just draw this stuff here before I start explaining, guys. Here, now, what's important now here is that each hydrogen molecule will occupy now, and you guys ready for it? Exactly the same volume as the nitrogen molecule occupies, exact same volume. So this volume and this volume is absolutely the same, guys. And so what's interesting now about this law is that even though this is a bigger molecule, guys, just in nature than this one, what's interesting, they're still occupying, guys, the same volume. And so if that's the case, which it is from empirical evidence, then if I have now a balloon of hydrogen, a balloon of nitrogen, as long as it's the same volume, guys, that we got here. So what I can now state is that you got the same, again, number of molecules in each. And if I have an empty balloon this, an empty balloon this, and I measure the initial masses, and then I pump the two gases inside, as long as, again, I pump the same, make the same volumes of each gas in here. So what that would give me, guys, the same number of molecules in each balloon. So when I weigh this one out and weigh this one out, when I now take the mass of this divided by the mass of this, I will reproduce, guys, the relative mass of nitrogen gas molecule to hydrogen molecule, as you guys going to see that relative mass in the periodic table. The periodic table is like 14.01 divided by 1.008. You're going to get the certain ratio there, the certain relative mass. So you will be able to get that mass by doing the experiment I just told you guys, explained you to do. And so that's where now, guys, one of the methods to get the relative mass now, to pretty much now build the periodic table based on the relative masses, because remember, the carbon now, guys, 12 isotope was selected as just arbitrarily, they just took carbon 12 isotope and made it just pretty much a standard mass against which they measured all the other elements. And so that relative mass, one way to do it is by what I just did with the balloons, guys, okay? So now this plus this, producing now, again, I'm gonna draw the same volumes here as for the gases I put before at microscopic level. And so this ammonia now will pretty much, guys, occupy now, guys, this small box here, NH3, the same volume as this, and as this gas, despite that the ammonia is more complex and supposedly supposed to have, guys, occupy a bigger volume. But in reality, it does not really, as long as it behaves, of course, as a ideal gas, which kind of we have to assume that ammonia behaves as a ideal gas, which is really at room temperature. It's not, because it has strong intermolecular forces than N2 and H2, of course. But again, for the now, just to explain this concept, I just, guys, you know, have to kind of simplify the concept here. But in a nutshell, the Avogadro's law, guys, importance is that no matter how big the gas molecules are on the molecular level, they will absolutely occupy the same volume. And that's kind of mind-blowing, because we would assume that if you have a bigger molecule, it will occupy a bigger volume, but it's not really true. And that's how you can figure out the relative masses, by measuring these balloons, as long as they pumping the balloons in each of the pumping the gas in each of the balloon, different gases, and as long as the balloons, guys, have the same volumes, you got the same pretty much number of molecules of each gas in the balloon. And then you can, guys, of course, I just explained you how to get the relative masses, and you can pretty much understand now how one way the periodic table was constructed based on relative masses, just using this Avogadro's law concept here. Now, what kind of problems you can get now in Avogadro's law? I'm going to go into your textbook now, and I'm going to check out the problems you got there. But as the problems will be as usual. You will be given, guys, 3 terms. You will have to find the 4th one. So let me just go into the Avogadro's law here. And by the way, remember, guys, how we done stoichiometry? Now, instead of the moles 3 to 1 to 2, you can now say that 3 liters of H2 gas reacting with 1 liter of N2, and then producing, guys, 2 liters of NH3. Because the reason you can say it, because all of these volumes for each of the molecules is absolutely the same, guys. So you can now, instead of using the moles, you can use actually the liter to liter ratio to figure it out, guys, the stoichiometry here, and figure it out, guys, the theoretical yield of the product, which is a gas. Now, so let me take a look now at example here. Let me just erase everything here. And we got here example here, 12.9. So let me, guys, solve this problem now here. So you got a balloon containing, okay, so the first piece of information, N1, 2.00 moles. And now of helium gas has a volume, so that would be my V1 here, 0.500 liters. And at the given temperature and pressure, remember guys, temperature, pressure here is constant. And then so if now N2 is equal to 0.48 moles of helium gas is removed from the balloon without the changing in temperature. So if 0.48 of gas is removed from the balloon without the change in temperature. So this is, let me just work on this. So the N2 will not be 0.48. Now I'm reading this question. I'll take care of it in a moment. Let me just read the whole thing here to take care of the N2 now. Temperature, pressure, conditions. What will be the new volume in liters for the balloon? So the N2 will be, in other words, 2.00 moles, because we are removing now 0.48 moles. So the N2 will be now the difference between these two. And that will, I'll do the mental math right now. It's going to be 1 point, looks like 5.2 here, moles of the helium gas, okay? So all I have to do now is the V2. And again, I will say that V1 over N1 is equal to V2 over N2, Avogadro's law. They want me to find this. V2 is equal to V1 times N2 divided by N1. So this is just cross multiplications. So now V2 is equal to, now V1 is given 0.500 liters times the N2, which is the new number moles, 1.52 moles, and then divided by N1, which is 2.00 moles. Moles and moles cancels out. All I have to do now, calculate, guys, a new volume, and that will be the end of the Avogadro's law. So now it's going to be 0.5 multiplied by 1.52, and then divided by 2. And so the volume, of course, decreases. I mean, it just makes sense logically, because so it's 3 significant figures. So I have to put another 0 here. Liters, it makes sense because if you guys are removing a certain number of moles now, you're removing now the pressure also from the balloon, and so the frequency of collision is smaller, and now balloon just going to shrink in volume. And again, I'm going to go, guys, into the explanation of each and every law that we covered here. We covered so far 4 different laws, and I'm going to use the kinetic molecular theory, guys, to actually explain now these laws based on this theory, even though the textbook does not really just vaguely mention this kinetic molecular theory, but I will go in a little more details so that you guys can have some conceptual understanding of how these laws operate. So I finished, guys, the 4 laws. We actually did some problems on these 4 laws. I'm gonna, after I explain, guys, in the next video, the kinetic molecular theory, I will go into the combined gas law, 12.6. I kind of went a little bit ahead, 12.7 I did first, and then I'm gonna do, guys, 12.6, and then I'm gonna finish up the remaining of the chapters. So I'll see you guys in the next video.